Welcome to this lecture on queuing systems, a crucial topic in stochastic processes and queuing theory. Have you ever wondered why some lines move quickly while others seem to take forever? Today, we are going to explore the mathematics behind waiting in lines. By the end of this video, you will understand how to analyze these systems and predict exactly how long a typical wait will be. Let us dive in. Now that we have introduced the topic, let us define what a queuing system actually is. Imagine standing in line at a busy grocery store. You arrive, wait your turn, get served by the cashier, and leave. This everyday experience is a perfect example of a queuing system. It is a mathematical way to study waiting lines. We use queuing theory to balance the cost of providing a service against the cost of making customers wait. A formal queuing system consists of an arrival process, a waiting area or queue, and a service mechanism. The queue strictly excludes the person currently being served. Before we move on, let us visualize this process with a clear diagram. On the left, you see the arrivals entering the system, driven by an arrival rate called lambda. These arrivals join the queue, which is the waiting line represented by the box with stick figures. Once a server becomes available, a customer moves out of the queue and into the service facility, represented by the circle. The server processes them at a service rate called mu. Finally, after the service is complete, the customer departs the system on the right. This simple flow is the foundation of all queuing models. With the basic flow in mind, we need a way to describe different types of waiting lines quickly. Mathematicians use a shorthand called Kendall notation, named after David George Kendall. It uses a series of letters and numbers separated by slashes, typically in a 5-part format. The first position describes the arrival process, or how customers show up. The second position describes the service time distribution, or how long it takes to serve someone. The third position is the number of servers working. The fourth is the system capacity, and the fifth is the total calling population. If the last two are infinite, we just use a 3-part code. Let us look closer at the specific letters used in the first two positions of Kendall notation. You will usually see the letters M, D, or G. The letter M stands for Markovian, which means the process is memoryless or completely random. This usually implies a Poisson distribution for arrivals or an exponential distribution for service times. The letter D stands for deterministic, meaning the time is exactly the same every single time, like an automated machine. The letter G stands for general, meaning any random pattern. So an M1Q means random arrivals, random service times, and exactly one server. Now that we know how to classify a queuing system, we want to measure how well it is performing. We call these measurements performance metrics. They tell us if the system is running smoothly or if it is about to collapse under too much demand. To calculate these metrics, we rely on two fundamental rates. First is the arrival rate, represented by the Greek letter lambda, which is the average number of customers arriving per unit of time. Second is the service rate, represented by the Greek letter mu, which is the average number of customers one server can finish per unit of time. This brings us to our first major formula, the utilization factor. Conceptually, this formula compares the amount of work coming into the system against the maximum amount of work the system can handle. We represent the utilization factor with the Greek letter rho. It equals the arrival rate lambda divided by the product of the number of servers C and the service rate mu. This tells us what fraction of the time the servers are busy. If rho is close to 0, servers are mostly idle. If rho is close to 1, servers are at maximum capacity. If rho is greater than 1, the line will grow infinitely long. Let us see this formula in action with a concrete example. Imagine a small coffee shop with exactly one barista working behind the counter. We are given that customers arrive randomly at an average rate of 10 customers per hour. The barista can make coffee at an average rate of 15 customers per hour. We want to find out exactly how busy this barista is. Since arrivals and service times are random and there is one server, this is an MM1 queuing system. We will set up our calculation using the arrival rate of 10 and the service rate of 15. Continuing with our coffee shop calculation, we plug our numbers into the utilization formula. For a single server system, the formula simplifies to just the arrival rate divided by the service rate. We divide 10 by 15, which simplifies to 0.667. This means the barista is busy about 66.7% of the time. The rest of the time, they are idle. Because this utilization factor is strictly less than 1, we know the system is stable, and the waiting line will not grow infinitely long over time. Beyond just how busy the server is, we care deeply about the customer experience. This brings us to the big 4 metrics of queuing theory. First is L, the expected number of customers in the entire system, including those waiting and being served. Second is LQ, the expected number of customers waiting in the queue only. Third is W, the expected total waiting time a customer spends in the entire system. Fourth is WQ, the expected time a customer spends just standing in the queue before service begins. These 4 averages give us a complete mathematical picture of the system. Let us look at the formula for the first of the big 4 metrics, L, the expected number of customers in the system. This formula takes the arrival rate, lambda, and divides it by the difference between the service rate, mu, and the arrival rate, lambda. Conceptually, that difference in the denominator represents the excess capacity of the system. This excess capacity acts as a safety margin that keeps the line from growing out of control. As the arrival rate gets closer to the service rate, the denominator shrinks and the number of people in the system grows very rapidly. Now that we have the formula for the expected number of customers in the system, let us apply it to our coffee shop example. We want to know how many people are typically inside the shop at any given time. We already know our arrival rate is 10 customers per hour and our service rate is 15 customers per hour. We substitute these specific rates into our formula. The numerator becomes 10, the denominator becomes 15 minus 10, which simplifies to 5. This denominator tells us the system can handle 5 more customers per hour than it is currently receiving. Finishing our calculation for the number of customers in the coffee shop, we divide 10 by 5. The math simplifies perfectly to exactly 2. This number represents the average state of the coffee shop during operating hours. It means that, on average, if you walk into the shop, you will see exactly 2 customers inside. One of those customers is currently at the counter ordering their coffee, and the other customer is waiting in line behind them. This gives the manager a very clear picture of the typical crowd inside the store. Now we move to the formula for W, the expected total time a customer spends in the system. Notice that this formula is very similar in structure to the formula for L, but it has a 1 in the numerator instead of lambda. It is simply 1 divided by the difference between the service rate, mu, and the arrival rate, lambda. This direct relationship between the number of customers and the waiting time is a fundamental rule in queuing theory. It allows us to easily convert between counting the number of people and measuring the amount of time they spend. Let us calculate this expected total time for our coffee shop customers. We want to know how long a typical customer will spend in the shop from the moment they walk through the door to the moment they leave with their coffee. We use the same arrival rate of 10 and service rate of 15. We plug these numbers into our time formula. The denominator is again 15 minus 10, which gives us 5. So our fraction becomes 1 over 5. This represents 1/5 of an hour spent in the entire system. Let us finalize our waiting time calculation. We have 1/5 of an hour. Since there are 60 minutes in an hour, We multiply 1/5 by 60 to convert it into a more intuitive measurement. The result is exactly 12 minutes. Therefore, a typical customer will spend 12 minutes total in the coffee shop. This includes both the time they spend standing in the queue and the time it takes for the barista to actually make their coffee. This metric is crucial for understanding customer satisfaction. Next, we look at the queue itself with the formula for LQ, the expected number of customers waiting in the queue. The numerator is the arrival rate squared, which shows how sensitive the waiting line is to incoming traffic. The denominator is the service rate multiplied by the excess capacity of the system, which is mu minus lambda. This formula specifically counts only the people standing in line, completely excluding the person currently being served at the counter. It helps managers decide how much physical space is needed for the waiting area. Let us apply this queue length formula to a scenario the text calls the car wash, though we are using the same coffee shop rates to answer a different question. The manager wants to know how many chairs to put in the waiting area. We use our arrival rate of 10 and service rate of 15. We substitute these into the equation. The numerator becomes 10 squared, which is 100. The denominator becomes 15 multiplied by the difference of 15 and 10. This sets up the arithmetic we need to find the average line length. Continuing our calculation for the queue length, we simplify the denominator. 15 minus 10 is 5, and 15 times 5 is 75. So we have 100 divided by 75. This simplifies to approximately 1.33. This means that on average, there is a little more than one person standing in line waiting to order. Since you cannot have a fraction of a person, you can think of this as the line usually having 1 or 2 people in it. To be safe, the manager should provide at least 2 chairs. Our final metric is WQ, the expected time a customer spends waiting in the queue before their service begins. This formula is very similar to the LQ formula, but the numerator is just lambda instead of lambda squared. It is lambda divided by the product of mu and the difference between mu and lambda. This formula tells us the pure waiting time. It completely ignores the time it takes to actually make the coffee or perform the service, focusing only on the delay the customer experiences while standing in line. Let us calculate this pure waiting time for our scenario. We want to know how long people actually spend standing in line before they even get to the counter to order. We plug our arrival rate of 10 and service rate of 15 into the waiting time formula. The numerator is simply 10. The denominator is 15 times the difference of 15 and 10, which we already know calculates to 75. We are now ready to divide 10 by 75 to get our waiting time in hours. Let us finish our final calculation. 10 divided by 75 simplifies to about 0.133 hours. To make this useful, we multiply by 60 minutes. Doing this shows that 0.133 hours is exactly 8 minutes. So a customer spends 8 minutes waiting in line. Notice that if we add the 4 minutes it takes to actually get the coffee made, it perfectly matches our earlier calculation of 12 minutes total in the system. The math is perfectly consistent. We have covered a lot of ground today. To summarize, a queuing system is a mathematical model of a waiting line, consisting of arriving customers, a waiting area, and servers. We use Kendall's notation to quickly describe the rules of the system. By calculating performance metrics like utilization, queue length, and waiting time, we can predict exactly how the system will behave under pressure. Mastering these concepts allows us to design better, faster, and more efficient services in every industry, from hospitals to telecommunications. Great job following along.